Hi and welcome to my presentation on the free fall of an object. The objectives of this presentation was to observe the motion of an object that is dropped from a rest and falls somewhat slowly, to construct a computational model where we consider simply the effect due to gravity, and also to construct a computational model where you consider both the effect of gravity and the effect of drag. I looked at a ping pong ball being dropped, and of course we have Newton's second law being applied. The final velocity is equal to initial velocity plus the net force over the mass by delta t. However, in this scenario, the net force is not zero, as we noted here, right? And the net force is equal to the rate of change of momentum, which is equal to the mass times the acceleration of the center of mass if the mass is constant. And in this case, our mass was constant. The first instance, we consider F net equal or due to gravity. So if we look at the code, we see the ball's mass here, we see G 9.8, and we have our vector in the y direction. We also have this weight vector. We had to put in this here in order to calculate the weight vector. When we ran our model, we obtained this part as shown here. And when we plotted our model against our experimental values obtained in Tracker, we see that the graphs match closely, where the red represented the experimental data and the blue represents the data from the model. In the previous slide, the model predicts a terminal velocity by evidence of the graph moving away from the initial curve to a more linear line. So we had that portion of the graph that looked more linear. The linear line portion represents terminal velocity where the net force becomes zero. However, even though the graph reflects it, the net force, which is equal to the weight of the object, cannot actually be equal to zero. Thus, the model cannot mathematically predict the terminal velocity. So a better model would include drag force. So again, we have Newton's second law, we have our momentum law principle. But in this instance, you're going to have F net equal to G plus the drag force, where the drag force is proportional to the velocity squared. Now, I use the same method of determining B constant as was stated in the video presentation that was given. Now, resistance to the drag is related by this equation here, so I assume that all these other terms, I call them B, and I had basically D is equal to minus BV squared. So as we can see it here, we have the drag force equal to minus B. Now, you cannot square velocity, a vector quantity, and velocity is a vector, but you can square its magnitude. So this is the code where we square the magnitude, and since the drag force is a vector, we have to put back this j hat portion here so that this will be a vector, so that this F net vector will be the sum of two vectors and not the sum of a vector and a scalar. So it's important that you had to put this minus j hat here, right? All the other code remained the same. So now F net is weight plus drag force. So this is the part we obtained from the model when we ran it. The blue line representing the drag, and of course the yellow line representing the weight. When we plotted the new model against the experimental data, we notice again that it follows very similarly as the first model. However, it's not an exact mirror. Right? Now what about terminal velocity? In this case, the second model also predicts the terminal velocity by evidence of the graph moving away from the initial curve to a more linear line. The linear line portion represents terminal velocity where the weight force equals to the drag force, and thus the net force becomes zero. So this graph shows all three, the two models and the experimental data, and we see both models closely map the experimental data. Right, so the graph where both weight and drag force contributes to the net force also closely follows the experimental data. Even though this is a better estimation, this graph also does not mirror the experimental data. Conclusions. The estimated value for the constant B was not accurate in that it did not reflect the true value of the other terms in the equation below. Thus, the exact value for the drag was not obtained by the model, which accounts for the points not mirroring each other. Conclusions. The experimental values were estimated based on the assumed center of the blurred positions of the ball, thus introducing error. The orientation of the camera was not perfectly straight by evidence of the curtain background not being totally straight, thus introducing error. Despite these errors, the models, however, in particular, where both drag force and weight contributed to the net force is relevant. What if? If the object was thrown down instead of released, there would be an additional force contributing to the net force. The net force would be the initial force in the throwing plus the drag force plus the weight. Hence, the displacement versus time for the computational model would be different to add to the throwing force. Therefore, the terminal velocity would be different. Thank you so much for listening to my presentation.